All right, you people. This is calculus 2 for those people actually watching the video again. All right, thank you. All right, make sure you smash that like and subscribe, all right? Notification button. Okay. Okay, they're up here. Oh, you can go ahead and donate to my PayPal account to, you know, I know, accepting tips, you know. Okay. All right, continuity. Now, okay, determine whether a function is continuous at a number. Determine the intervals in which a function is continuous. And properties continuity, use intermediate value theorem, IVT. All right, continuity definition, at a number, a function is continuous at a number C if the following three conditions are met. Okay, I would like highlight or do something to, you know, these conditions are met, because these are important right here. So even if you already know this. So f of C is defined, that is C is in the domain of F. So it has to be there, right? If the limit of x, as x approaches C, f of x exists. So if it exists, it's good, right? If it exists, yes. And the limit as f x approaches C of f of x is equal to just f of C. So the limit is equal to the function. That's what that means. The limit is equal to function. So let's take a look right here on A. So on this first one right here, so the left hand is right here is equal to the right hand, right? So yes? Yep. Okay, so if the left hand is equal to the right hand, what does that tell me? The limit exists. Now, the limit exists at C right here, and they're both going to that number right there, yes? So the function f of C is equal to the limit, isn't it? Yeah. There we go. So this one does work. Okay, what about this one right here? The left hand and the right hand go to the same thing, right? The left hand and right hand both go to the same number. Okay? So on this one right here, and it is not equal to f of C, is it? Since this one is not equal to f of C, does this actually meet this third criteria? No. Nope. Okay. All right, next one. Right here, left hand and right hand both go to the same number, but f of C is not defined. Okay, so is that one going to work? Say no.
Yeah, no.
No. Okay, because right here, look at the first one. It says, but part of this third one specifically says f of C is not defined. Yeah. So there's the first rule. That one does not like that one, right? So we do not like that one here or there. We do not like that one anywhere, except for in these portions over here. Okay? All right, so this fourth one right here. Fourth one. Left hand goes to one number. Right hand goes to a different number. What does that tell me about this?
It just doesn't exist.
The limit does not exist.
Yeah.
Okay, so what criteria does that get rid of? The second one. The second one says that one does not work. So is that continuous? No. Okay, good. So this one right here is not continuous. All right, so this one right here, the fourth one right here, the left hand and right hand are both going to the same number. Are they? No, they're not going to the same number. So which one does that get rid of? The second one. Oh, not the second one right here. Okay. Yeah, actually you're right. Yeah, I'm sorry. Yeah, I'm sorry. No, I'm sorry.
It's two.
It took me a second. Yeah, it's the second one, and this one right here is also third one, right? Why is this third one? Okay, so limit right here. So f of x is equal to f of C. Is it equal to? There's no closed dots there, right? Okay, and the first one also. So this thing right here says f of C is not defined.
Yeah. Okay,
so yes, good. Okay, I said highlight those for a reason, so I'm hoping you guys are. Determine whether a function is continuous at a number. Alright, let's see what we got here. We have, telling you guys highlight stuff, but I need 3 highlighters. You guys want some highlighters? 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 There we go.
Oh, we can share one.
Anyone else?
You understand.
I got one more.
Yeah, my bad. I do the whole time.
Okay. All right. So, okay, is this one going to be continuous at 1? Is this one continuous at 1? Is there any restrictions here? Is there any restrictions in the domain?
No.
No, there's no place in which that this one's going to be undefined.
Yeah.
Okay? There is no holes, there's no gaps, there's no piecewise. Is this one going to be continuous at 1?
Yes.
Yes. Okay, what about this one? On B? Continuous at 2.
No.
Now, is there any holes or gaps?
There is.
Okay. Okay, so what is there? Is there a hole?
Oh, actually.
Yeah.
Okay. There is, isn't there?
At 2, exactly.
At 2, right?
Because you plug in 2, it's just going to be 0 in the denominator.
Okay, but then will I have anything in the numerator?
Yeah.
Is there an asymptote here? See, yes.
Yes.
There is an asymptote. Is it horizontal or vertical? Yes. Maybe?
100%.
What's the degree of the top? Okay, what's the degree of the bottom?
2.
What does it say if it has the same degree? Okay, so where do I have one? Okay, so is that a horizontal or vertical? Horizontal. That one's horizontal. Okay, so this one right here. So this one continuous at 2. Is this one continuous at 2? No. Okay, because this one right here, when I plug it in there, I'm going to get 0 in the denominator. Okay, so it is not continuous at 2. Okay. Whether a function is continuous at a number right here, continuous at -2. Is it continuous at -2? Come on, class. No, why? Because the bottom, right? Denominator? So, no there. Okay. What about 0? Is that continuous there? So 0, 0, so it's going to be rad 2 over -4. So that is a number, right?
Yeah.
So, okay, so that one's going to be continuous there. All right, so what about +2? Nope. Nope. So the only place continuous is at 0. Here it is right here. So at my -2, I have my asymptote. At +2, have another asymptote, but it is continuous at 0. Okay? Determine whether piecewise definition is continuous. Determine it is continuous at 3. All right, for it to be continuous at 3, that all parts have to go to the same number. Okay, so let's see. If I plug in 3, so if I plug in 3 for this one right here, what's it going to be?
Well,
So numbers that are less than 3, what do we get? Do I get 0 over 0?
Yeah, it's undetermined. The first one.
Indeterminate? Okay. What is 0 divided by 0 anyway?
Indeterminate?
That's Siri.
Siri, what's 0 divided by 0?
Oh, is it the Cookie Monster?
Yeah.
I don't know. I'm asking you.
No, because basically she gives you a sad story about how you have no friends to share no cookies with. And the Cookie Monster's sad because he has no cookies, and you're sad because you have no friends.
Let's just fast forward a few days and just use the L'Hopital's rule and just.
You know, we're not yet. We're not finding derivatives yet.
Oh.
All right. I know there's a calculator out. Someone's using it. What is 0 divided by 0?
Oh, it's undefined.
There we go. Thank you. That's what we're trying to get to. Okay. If you're ever having trouble with something like that, just plug it in. See, be like, oh yeah.
That's not a
Okay, it's like ln1. You guys know what ln1 is?
Ellen?
ln1.
Or is it undefined? It's undefined.
So what is ln1? Thank you. Okay. So stuff like that, things that are identities and stuff like that, you got to try and remember those. So anyway. All right. So we got that issue. All right. What about this one right here? So if x is 3, this is 9. Okay. X is 3, this is 9. What about this side right here? This is going to be 9 minus 3 is 6. So is the limit going to exist here?
Yes. But the third point is the limit as x approaches c of f of x is not going to equal f of c.
Very
It's
good.
going to be 6. But
So the f of x is not going to work, right?
Yeah.
No. Okay, because right here it's 0 over 0. I really can't even say much over this piece right here. I'm just looking at the second and third. Are they going together? Is the function f of x equals f of c? Not really. No. So this right here. So I'm going to graph this real quick so you guys could actually see what it's going to look like. So now, right here, go to my graph. Okay, go to here, and I want I think I have to do, there it is.
Ooh.
Okay, so this is control,
Oh, no.
divide. What was the problem?
X squared
X squared
minus 9
minus 9 over,
x minus 3, I think, right? Yeah.
say x,
Minus 3, because if you plug in 3, you know
okay, and so this is where x is what?
it's gonna be less than 3.
Okay, and then next one, go too far. What's the next one? 9, right? So when x equals 3, and next one,
X squared minus 3. Right.
where
Greater than 3.
okay, so let's see what it looks like.
Wow.
it's almost continuous.
I
I can't believe that it's not continuous.
I can't believe it's not butter. Okay, so it looks like it's continuous, and this is the reason why we did this on a graph. Okay, for this case right here, why is it not continuous?
Because f of c is 9, where it should be 6.
Very good. So let's take a look. So if I was actually, remember the other day I showed you menu, trace,
And then you plug in the number.
yeah, plug in the number. So right here,
In the middle of nowhere.
so at 0, it's okay, it's following along, blah, 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 blah. All right. Blah, blah, blah. All right. Just plug in the number 3, hit enter, and it comes up and it's not on my line, right?
Yeah.
Okay, so it's not continuous because there is a hole right there, okay, in the graph. If that middle piece right there of my piecewise was equal to 6, this could be continuous. Okay, it could be continuous. All right, so let's take a look at next, where am I here? There we go. All right. Okay, definition, removable discontinuity. Right here, the number C is called a removable, oh wait, hold on. Let f be a function that is determined everywhere in an open interval containing C, except possibly at C. Okay, the number C is called a removable discontinuity of f if the function is discontinuous at C, but the limit as x approaches C exists. The discontinuity is removed by defining or redefining the value of f at C to be the limit as x approaches C of f of x. In words?
If it's a hole.
In
Factor it.
In English.
Just factor it. Can you cancel out? So if I have like an x plus 2 on top and an x plus 2 on bottom, I could cancel those out, right?
Yeah.
So the negative 2 would no longer be a point where it's discontinuous because I took out the part in the denominator, which would make it discontinuous. But I would still, okay, that's just by removal discontinuity. Okay, you still, when you're dealing with this, you're dealing with the original function. Okay, so it still has a problem at negative 2, but we're able to remove the discontinuity for this. Okay. All right. Okay, stars. Okay, what's this thing right here called?
Absolute value.
No, it's not absolute value.
It's this floor.
Yes, it's the floor function. So this is
The rounding to the lowest value.
it's a floor function.
Yeah, no, it's like right or something.
Starts with G. It's Muhammad Ali. What does Muhammad Ali always say? That he is the what? The greatest. Greatest integer? Trying to remember where this one is. Scape. Let me clear that. This one would be. Is it that one? Oh dang it! Tab. Nope. It's on here somewhere, I just can't see it.
Oh, it's the left bracket, the left parenthesis.
Right here?
Yeah.
So control, there's that one.
Oh, that was wrong bracket.
Yeah, that one's the actual,
That's just a straight up.
Never mind.
no, not that one.
You're looking for the symbol that's around.
Alright, so thank you Google. Okay, so I did integer x.
Create slider. This is create slider for?
No. Okay, so let me menu. Okay, window, gonna go standard here so I could actually see it. So now it gives me a bunch of little lines here. This is step function. So that means that it's goes here until it actually gets to the next one and it stays there as we keep going. So right here on the graph, is this one continuous here? No, it's not continuous. Let's look at the question now again. Okay, so continuous. So I'll let you guys work on that information. All right, let me go back to here. So star's yours. Okay, right here. All right, so one-sided continuity at a number. So let f of x be defined interval. So what does the parentheses mean? What's this parentheses right here mean? Is it included or not included?
No.
Not included. So it's not included. Not going to include A, but does it include C?
Yes.
Okay, it includes C. Then F is continuous from the left at C, because it's including C here, right? So the left, here's that. Now function be defined as an interval. Now it's including C again, and it goes to the right. But is B included?
No.
No. It's continuous from the right at this right here. So now if the left and right are continuous, then for this case right here, and it is including it there, then it could be,
Then why not?
yeah, then it should be equal to. So the function does exist, right?
Yeah.
Okay. So let's take a look at the next one. Intervals. Okay, so stars Okay, this is important for you guys.
Yeah.
Actually, there's no work on this one. This is just important for what you need here. And so that previous page goes with this one here. All right, determining whether a function is continuous on a closed interval. Closed. Okay, so is this one going to be continuous on a closed interval? So at -2, is it allowed at -2?
Yes.
Mm-hmm.
Yeah.
Yeah?
Yeah.
Square root of 0 is 0, right? Okay, so that one's continuous, right? So, and what about at +2? Okay, there's my closed interval, right? So is it allowed over this whole thing right here? So this should look like some type of like half circle thing like this, right? Where I got -2 and I got +2 here, something like that, right?
Yeah.
Okay, should look like that. So it is continuous. Is it? Yes. Okay. We can include those ends. Definition, okay. Determinant function, continuous every number at C in the domain. Okay. Joy. All right, theorem to go along with it. So a polynomial function is continuous on its domain, all real numbers. A rational function is continuous on its domain. If a function is continuous on an interval, its graph has no holes or gaps on that interval. Okay. If a function is continuous on its domain, it will be continuous at every number in its domain. Its graph may have holes or gaps at numbers that are not in the domain. See, let's go back to the previous one. So, over its domain, the domain of this one is from -2 to 2, right?
Yeah.
So what if I say -5?
I mean, evidence.
Would that work?
No.
No, it wouldn't. It wouldn't work, but it's outside of its domain, right?
Yeah.
So the domain of this, it is continuous over its domain. So it is going to be continuous. Okay? Things outside its domain, it's not going to matter. Okay? Here's some more. Right here. Theory of continuity, composite function. Continuous at C, and a function f is continuous at g of C, then the composite function f of g of x equal to fg of x is continuous at C. That is the limit as x approaches C, f of g of x. Okay, I could take like this, or I can separate it out. So I find the limit of g and then put it in there for x. That's what it basically means. So whatever it is for g of C, I plug it in for f to get that number. So what rule does that look a whole lot like? There's a rule that it looks a whole lot like. Yeah, looks a whole lot like chain rule, right? Of the inside times the outside, right?
Oh, yeah.
Yeah, okay. If f of f is a one-to-one function, is continuous on its domain, then its inverse function, f of inverse, -1, is also continuous on its domain. Okay. So this one's intermediate value theorem, and I'm going to work on this one tomorrow. Okay. I'll give you guys time for that. Don't forget, like, subscribe. Okay, all that good stuff, right?